Hello everyone, in this video we will discuss about a problem on topology.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So consider the following topologies. T1 is the standard topology. Standard topology means it is the topology generated by basis, which is a collection of all open intervals in R. Open intervals are nothing but of the form sets of the form A comma B. All the collection of these intervals will form the basis for this topology. And the topology of Rk. So first, defining K, it is nothing but 1 by n, where n belong to positive integers. Like 1, 1 by 2, 1 by 3 and so on. Now consider the collection of all open intervals A comma B and A comma B minus K. Okay, you just take out the K elements in K from the open interval A comma B, and you also consider just the open interval A comma B. The collection of all such intervals will form the basis for the topology T2. And T3 is the finite complement topology. So this means that R minus C belongs to T3 for all finite set C. Basically, it means that every complement of a finite set is an open set in this topology. So that defines the finite complement topology. And T4 is the upper limit topology, in which you have the sets A, open A to closed B as the basis. And for T5, the basis is like minus infinity to A. So all the elements less than A will form a basis. So you can try proving yourself that all these are indeed a valid basis for the topology, so that you can do it as an exercise. But let us look at what they are asking for. You are supposed to determine which of the others the topology contains. For example, it might happen that T1 is contained in T2. T1 is a subset of T2. Right? So that's what they are asking for us to look. So there is a famous idea using basis of these topologies to interpret that. So suppose if the idea goes like this, suppose if you have a set X, say two topologies are defined on it, T1 and T2, with basis curly B1 and curly B2. Suppose if I can prove this, that is, for any basis element, if you take any basis element B in curly B1 and any element X of capital B, then suppose there exists a basis element B prime, suppose there exists B prime such that X belong to B prime, and B prime is a subset of B as depicted here. B prime is a subset of B, and B prime is a basis element of the topology T2. That is, B prime is in the curly B2. Then we say that the topology T2 is finer than T1. Topology T2 is finer than T1, or you can also say T1 is a subset of T2, which means any open set in T1 is also an open set in T2. This is due to the fact that for any basis element and for any element of that basis element, there exists an basis element that is a subset of that and containing that element. Which means for any open set which is formed by, which is nothing but a union of few basis element, it is also a union of few basis element of B2. So it is also open in T2. So that's why T1 is a subset of T2. So using this idea, let us consider the topologies T1 and T2. T1 is the standard topology and T2 is the RK topology. Suppose if you, in the real line, you take the basis element B of, so consider any basis element B which is of the form A comma B of T1. Okay, it belongs to T1. Then we know that A comma B, then for any, suppose for any X in A comma B, and let B prime be also equal to A comma B, which is also a basis element of this is B1 and B2, curly B1 and curly B2, which is also a basis element of T2, right? Now you can easily see that X belong to B prime, which is a subset of B. So for any basis element and for any element of capital B, you have a capital B prime which is a subset of B, and that capital B prime is a basis element of T2. Now this implies what? The topology T2 is finer than topology T1, or T1 is a subset of T2, where T1 is standard topology and T2 is RK topology. Now we will try the other way around. Is it true that T2 is a subset of T1 or T1 is finer than T2? Let us try to see. Suppose if you consider in the real line, let us draw the real line and consider the open set, the basis element. Let's say now B is considered to be 0 to 1 minus K, which means you just drop these elements 1 by 2, 1 by 4, 1 by 3, and then 1 by 5 and so on in capital B. So this is a basis element of T2 topology. Now consider Z, obviously let us not only take till from 0, let us take from minus 1. Then minus 1 to 1, where minus 1 and 1 are excluded, except the K is our open set. So basically like this, something like this, except the K's. So now, is it possible to find a basis element that is find a basis element of topology T1 that is containing 0 and entirely contained in capital B? That is this set. Is it possible to find? it is not possible, because say you take a basis element b naught, which is of the form some a comma b, and that contains 0, which means a is negative and b must be positive, right? But in any case, if you consider that since b is positive, I can say b is greater than 0. But since this number 1 by n is dense, in the sense they are dense closer to 0, that is, I can always find there exist n in natural numbers such that 1 by n is less than b. Because for some large n, 1 by n will go lesser than b, right? Because b is a fixed. For a fixed basis element, I can always find 1 by n less than b, which means implies 1 by n belongs to b naught, but 1 by n do not belong to b, because b is minus k, right? So that imply b naught is not a subset of b. So for any basis element in T1, it is not going to be containing 0 and entirely contained in b, which means T1 is not going to be finer than T2. So that we know. Now consider the topology T4, suppose. Let's now consider the upper limit topology T4. So, and let us compare T2 and T4 now, which is the RK topology and the upper limit topology. So first let us again consider a real line, and if you consider any sets of the form a comma b, then for any element x in a to b, I can always take, suppose if you consider b to be a comma b, then I can always take my b naught, so this is from basis element of 2, I can always consider a comma x closed, which is a basis element of b4, and for any x in a to b or in capital B, I can say x belong to b naught, which is a subset of capital B. So for this form of basis element, I can always say that there is a basis element in B4 contained in it. But B can also be of the form A to B minus K. Right? In that case, what will you consider B naught to be? So in that case also I can find the B naught given x. Suppose say the x is like this. X belong to capital B. Then I can always find a 1 by n value if at all it is present. Say 1 by m value, such that so either I will be able to find this, which is 1 by m is less than x and x is less than 1 by m plus m minus 1. Or, okay, in this case, I will take B naught to be 1 by m to x closed. Or you can see that there is no such m inside, and this is greater than a. And if there is no such m, then I can always take a to x closed to be my b naught. In either case, b naught is a subset of b, because there are no 1 by n values in between in this interval. And again, if there are no 1 by n values between a and x, I can directly take from a to x, because there is no minus k here. So, and also x belongs to b naught. So this implies what? T4 is finer than T2. You can try the other way around and you will get a contradiction. In order to prove that T2 is finer than T4, or in taking a basis element of T4, say from A to capital A to B closed, is it possible to find a basis element in T2 which contains B and is entirely contained in A to B? And that is never possible, because if you take any, say, C to D which contains B, then that implies D is greater than B. And we know that any basis element is of either of the form C comma D, but obviously C comma D, over here B is from A to B. Obviously C comma D is not a subset of capital B. So I have to, let us consider then C comma D to C comma D minus K. Again, this is not a subset of B, because there would be some irrational numbers also in the interval B to D, right? So those irrational numbers is in B to D. Let's say that irrational number is R, but that irrational number do not belong to A to B closed, and that, whereas that irrational number belong to C to D, which implies, C to D minus K. So C to D minus K is not a subset of B. So that implies T2 is not finer than T4. So hence we cannot say the other way around. So now we have arrived at T4 is finer than T2, which is finer than T1. Now only the things to consider is T3 and T5. Now if you consider the topology T3, which is the finite complement topology, with T1, I will tell you why am I comparing it like that, because you will directly get T3 to be finer than T1 to be finer than T3, which means T2 is finer than T3 and T4 is finer than T3. Right. Now, if you consider any finite set, let's say C is some finite set, C1, C2 till Cn, and you consider the complement of this, which is the open set. So let us take C1, C2, C3 till you have Cn, and you take the complement of that, which are, let me highlight that, which are these intervals, and like this, these intervals, or the complement, say Cn minus 1, and like that. Now if you take so this is an open set, we will prove that this open set is also open in the topology T1. Suppose if you consider any element x. I can say, for example, here Cn 2x plus 1 is an open set, is an basis element in 1, which means it's open in T1. And it is a subset of this open set. Right? So similarly, I can take any x. For example, you can take x to be here, in which case you will take b prime to be C2 to C3, which is again belonging to the basis element of topology T1. So from this, I can say that x belong to b prime, which is a subset of R minus C. So hence, for any element of any open set, there exists a open set in T1, which is a subset of the open set in T3. So then it is trivial that R minus C belongs to the topology T1, because I can just take the arbitrary union of all such b primes, right, which will form R minus C, because every b prime is a subset of R minus C. And I can make b prime to contain all the elements of R minus C like this. So hence, turns out that T4 is finer than T2, is finer than T1, is finer than T3. But is it true that T3 is finer than T1? That's not possible, because if you consider, let's say, you consider a basis element A to B. If you want a open set in T3 to be entirely contained in A to B and containing some x, suppose, then the complement of that must be finite, right? That's how the finite complement topology is defined. So the complement of that will not be finite, because as you could see here, minus infinity to A union B to infinity is a subset of the complement of U, where U is where U is a subset of A to B and it contains x. Now obviously, minus infinity to A cannot be a finite set, it must be infinite, right? Because it does not have any minimum, so it must be infinite. But that is a contradiction, that any complement of open sets in T3 is finite. So that is not possible, that T3 is finer than T1. So this is the order of topologies. Now if you come to the topology T5, we can prove that we know that T5 has basis of the form. It is the collection of all sets of the form minus infinity to A. right? So in this topology, if you consider any basis element minus infinity to a contains all these elements, but it will not contain a. Now take b to be any, it can take any basis element. I will prove that T1 is finer than T5. In the sense, if you take any element x, then obviously B prime could be minus x minus 1 to a, which is a basis element in B1, right? Minus x minus 1 to a is a basis element in B1 because all open intervals are basis element in T1. And it also contains x. Why it also contains x? Because this value is less than x, whereas this value must be greater than x by definition of x. So what do we see here is that it is always a subset of, what do we see here? I can always find B prime in B1, which is a subset of B. For any B in B5, I can do this. And that implies T1 is finer than T5. But T5 is not finer than T1. It is so simple to prove. If you take any basis element a comma b of T1, and if you consider any element x of a to b, then any basis element of T5 containing x will be of the form minus infinity to some number c, where c is greater than x. Now, since c is greater than x implies c is greater than a, and that implies a minus 1 belong to b prime because c is greater than a, right? But a minus 1 do not belong to b, implies b prime is not a subset of b. So you cannot find an element b prime which is a subset of b and containing x, which imply T5 is not finer than T1, and hence we get this relation also, that T1 is finer than T5, but already we know that T1 is a subset of T2 and T2 is a subset of T4. So hence we have got two relation. T4 is finer than T2 is finer than T1 is finer than T3. Now we are yet to compare only T3 and T5. As an exercise, you are asked to prove that T3 and T5 are not comparable, and put in your ideas in the comment section. So see you in the next video. Thank you.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.